Now, the thing about science is if someone says something or makes a theory that sounds like it's preposterous, even if it's Einstein who's saying it, we, well, for every theory, we just need proof to show that it happens. Some things work well in theory. If it doesn't match up with experiment, we can't use that theory anymore. So, um, what we needed to do was to have some proof that particles behave like waves with a wavelength that is predicted by de Broglie's equation. And when we say acts like a wave, we need some of those wave-like properties, some of the phenomena that are explained through waves. Um, and the one we go for is diffraction. Okay. Um, we looked in previous lessons at light, and if we put light through a diffraction grating, and where the gaps are small enough between them, we get kind of a pattern then on our screen. Okay, so this is our diffraction grating, um, where we'll get like a bright central fringe, and then we'll get an n equals 1, and then we'll get an n equals 2, and the same on the other side. Um, and this will be our laser light coming from our laser. We've done that experiment, okay? We've seen the results of that. What we want is to be able to do this, but instead of using light, we use particles, or what we used to call particles. And we want to get the same results. So what we did is instead of using laser light, we use electrons. And we accelerate them by making them be attracted to a positively charged plate that has a tiny little hole in it. The electrons go flying through there, so they're now moving quite fast. We can work out their de Broglie wavelength by using our equation. Okay, and then we need a gap, if you remember, for diffraction, where the wavelength is roughly the same size as the gap. Now that gap's quite small for these electrons traveling at those speeds. So what we do instead of using a diffraction grating or a tiny little slit for them to pass through is we just use a mesh of atoms. Okay, so we use carbon atoms in graphite, and the gap between the carbon is of the right amount to get expected diffraction. Okay, it's the same, the gap is the same size roughly as the de Broglie wavelength. So we can get from that an expected pattern. The only difference here is that all those layers of the graphite won't be perfectly lined up. So not only will it be diffracted, say, left to right along the horizontal, it'll also be diffracted up, down, and at every single conceivable angle in between those as well. So this is our little setup where we have a little kind of filament at the end that we heat up using a small voltage, just 4.3 volts, but it heats it up enough that an electron can escape an atom. It's called thermionic emission. It's then attracted to this positive charged anode over here. So this gets accelerated. It's now an electron beam. It will have a de Broglie wavelength by our equation. It goes through the target, which would be carbon graphite, and then we expect to get diffraction. Now we can't see electrons, but what they do is they hit into the screen over here. This is made of a special material. The electrons transfer their kinetic energy to it. They cause electrons in the atoms in that material to go up in energy level, and as that happens, they then drop down and they emit light. So essentially all this screen does is just a fluorescent screen. Wherever the electrons hit, you'll see a little dot of light. So by looking at where the light is on that screen, we can tell where the electrons have been. Okay. And if we were dealing with just diffraction along one plane, so it was through a slit, we get like a central bright fringe, and then we'd get dark bands and then bright fringes again, something like that, either side of our central one. But remember, this isn't just going to be diffracted left and right, it's going to be diffracted up and down, and everything in between. So in fact, what we see is, rather than fringes, it's not very well drawn, but it'll do, we get bright and dark rings. Okay, so we get a bright dot in the center, and then we get bright fringes after that. And when we do this experiment, that's what we get. We get electrons behaving like they're waves. Why is this dark here, this bit here? Because no electrons can get there. Why can no electrons get there? Because of total destructive interference, a wave-like property, but applying to our electrons. What we then do is we make some changes. Okay, so we use a higher voltage, which means the velocity increases, which means their momentum increases. But the effect of that is, if the momentum increases, the effect on our de Broglie wavelength is it decreases. And if the wavelength's now smaller compared to the gap between the atoms, we get less diffraction, which means the light will be less spread out. So rather than getting a pattern like this, we get rings that are closer together. Okay. So when we use a larger voltage, it goes from this pattern, which was good enough evidence for the electrons behaving like waves, and we get this, the thing we would predict if we used a larger voltage, which produces a larger velocity, which produces a smaller wavelength, and we get less diffraction. Okay, so that is our proof for wave-particle duality, where waves sometimes act like waves and sometimes act like particles, and particles sometimes act like particles, but also sometimes act like waves.